Okay, so the big ideas for topic 2, be on the lookout for these as we go. What is variation? What are adaptations? Why is an adaptation likely to start appearing more in future generations? What is gradualism? And what is punctuated equilibrium? Okay, so we start today off with adaptations. So what is an adaptation? It's anything that makes an organism better suited to its environment. I'm going to add to this definition a little bit because, yes, it makes it better suited to its environment. But really, what does that make it do? It makes it more likely to survive. If you're very well suited to your environment, you're likely to survive. And not only that, but reproduce. That will be important later. Okay, so an adaptation makes you suited to your environment so that you are more likely to survive long enough to reproduce. Now, there are two main types of adaptations. Okay, there are structural adaptations, which are actual physical features of the organism, like body parts basically, that you can point to and say that thing that it has gives it an upper hand in survival. Okay, so just some examples. A beaver's flat tail, right? That helps it to swim faster. It acts like flippers. You can see why a beaver would want to swim faster, right? It helps it gather food more quickly, helps it build its shelter, all that stuff. A rose's thorns protect it from grazing animals, right? That's a structural adaptation. Makes it more likely to survive because not many things are going to want to eat a prickly rose. A snowshoe hare's white fur helps it hide from predators, right? Camouflage. Now it blends in. If a fox is looking to eat a hare, they can't find it as easily because it's white on a snowy background. And then there are behavioral adaptations. Those are things that an organism does to survive, right? These are, well, behaviors that it has, right? So you can't necessarily just point at one and say, oh, look, that's an adaptation, unless it's currently doing the thing. So, for example, birds fly south in the winter. Why? Because, well, in the winter, a lot of the stuff they like to eat is going to die off and they won't be able to eat. So they fly south to get more food, making them more likely to survive to reproduce. Bears, they can hibernate. Again, kind of a similar reason. In the winter, the food's going to die off that they like to eat. So instead of wasting a bunch of energy when there's no food to replenish it, just go to sleep for 6 months. Save that energy for the spring when there will be more food again and you can eat it. In deserts, you find a lot of nocturnal animals. Nocturnal meaning they only come out at night. Why would that be a good idea in the desert? Well, it's so hot during the day. If it's hot, you're losing energy just to keep your body temperature regulated. And if you're using energy, you're losing water, right? So animals avoid losing all that excess water, which is hard to replenish in a desert, by only coming out at night when it's cooler. Makes them more likely to survive and reproduce. Behavioral adaptation, something they do that helps them stay alive. Okay. Now, most adaptations, pretty much all of them, serve at least one or more of these three purposes. So they help an organism get food. Yep, that definitely helps you stay alive to reproduce. It helps you not become food for someone else. Yep, definitely helps you survive to reproduce. Or it just straight up helps an organism reproduce, right? That is an adaptation. If it helps you survive to reproduce, it is an adaptation. So obviously something that's going to help you reproduce would be considered an adaptation. So just to get thinking about adaptations here a bit, let's look at some for an organism. How about a polar bear? So a polar bear is an example of an organism that has adapted well to the cold Arctic. So we got to keep in mind they live somewhere cold and somewhere that's always snowy. Keep that in mind. It's a carnivore that primarily eats seals, and they usually hide and wait near breathing holes in the ice to capture seals when they come up for air. So knowing what we know about a polar bear and the environment it lives in, let's think about some different adaptations and how they help. So a polar bear has slightly webbed toes. First things first, is that a behavioral or a structural adaptation? Is that something it does to stay alive, or is it a physical feature it has that helps it stay alive? Well, it's its toes, right? That's structural, okay? Now, as we said, adaptations are not just features about you, right? They're not just things that you might like about yourself, right? They are things that help you survive to reproduce. So if they're telling us slightly webbed toes are an adaptation, they must do something that helps the polar bear survive. So what could be the reasoning that that would help you survive? Well, for a polar bear living in the Arctic, right, and we've seen they hunt seals that are in the water, webbed feet can help you swim faster, for one. But another big one is that it kind of acts like a snowshoe almost to keep them up on top of the snow so that they can run really fast if they need to, and also they can stalk a little less clumsily. That will definitely help you survive. Okay, white fur, structural or behavioral? Is white fur something it does to keep itself alive? No, right? It's something that it has, a physical feature that it has. So that is definitely structural as well. Why would you want to have white fur if you're a polar bear? Again, for camouflage, right? Just because it doesn't need to hide from predators very often doesn't mean it doesn't want to hide, right? It wants to sneak up on its prey. Remember, all adaptations serve at least one of those purposes. So in this case, helps it get food. If it can sneak up on prey, that's going to help it get food. Okay, a thick layer of fat and black skin beneath translucent, which just means partly see-through fur. Why would a polar bear want to have a thick layer of fat and dark skin and slightly see-through fur? This one's a bit of a thinker. You might have to think back to geology a bit too when we talked about albedo. Remember, it lives in the Arctic. The Arctic is famously cold, right? So that fat, that layer of fat, is going to help insulate it so it doesn't lose too much heat to the environment. Because remember, heat is energy. You don't want to be wasting the energy you got from eating a seal on just losing it to the cold environment, right? So that fat helps keep that in. And then remember, albedo, the fact that the polar bear has dark skin actually helps it absorb more sunlight. And so the little bit of sunlight that it gets up in the Arctic, it can actually do a better job of keeping it warm and therefore not losing as much energy to the environment as its body tries to come into thermal equilibrium with its surroundings, right? Which just means become the same temperature as. But again, they're all structural. And again, that translucent fur is just going to let more sunlight through in the first place. Okay, females hibernate with cubs until spring. Why is that a good idea? Well, cubs are a lot of mouths to feed, right? Not to mention your own mouth. So, just like the bear we talked about on the last page, if you can hibernate during the winter when there's not as much food, when holes in the ice are not going to be as abundant because there's going to be more just frozen solid ice, well, go to sleep for a few months. And then in the spring, when there's going to be more opportunities to hunt and eat, then wake up and worry about feeding yourself. Now, is that behavioral or structural? Is that a physical feature of the polar bear or is it something it does? It's something it does, right? It's a behavioral. Okay, can stand up on hind legs. Now, the wording of this is a little, kind of leads me to say two things. So, yes, standing up on hind legs, that's definitely something it does. That would be behavioral, right? But the fact that it can stand up on hind legs, that kind of is structural. You have to have the right bone structure to be able to stand up on hind legs. Okay, so I'm going to say this one's kind of both, depending on which part you're focusing on. So standing up is definitely a behavior, but being able to stand up is a structural. Either way, how does that help it survive? Well, if you can stand up in the Arctic, which is relatively flat, you can see a long ways. You can see lots of prey. You can see even potential predators, although there's not many predators for a polar bear other than humans, right? But you can see all of it. Okay, I love this one. It's really cute. Covers its black nose when it's hunting. So behavioral or structural? Behavioral. It's something it does. Okay. What would be the advantage of that? Well, its white fur is pretty good camouflage, but the black nose kind of wrecks it, right? You would see a black dot kind of approaching you if you're a seal, and you might dive back down into your hole. So it literally will take its paw and cover its black nose while it's hunting so that it's more camouflage to prey. Okay. So all of those, most of them really help it get food, right? But some of them also will help it not become food too, which makes it more likely to survive to reproduce. Adaptations. Okay, so we're going to take adaptations now and talk about how they fit into changes within populations. So in the fossil record, we study something called morphology. What's morphology? It's just the shape and form of an organism. So you could say that the morphology of human hands is that they have 5 fingers, right? You could even start describing the average length of the fingers, the number of knuckles, stuff like that, right? That's all morphology. And we can look at the morphology of thousands of generations by looking at the fossil record of some species. We can go back and say, okay, a few generations ago, the morphology was different. The fingers were a little longer, or they only had 4 fingers, maybe even, right? Essentially, the fossil record provides a record of, well, not all life. So obviously, not everything becomes a fossil, but we can see life very far back and pretty consistently through the fossil record. And so if evolution is occurring, the morphology of organisms throughout the fossil record should be different than the ones we see today. And spoiler alert, they are. The fossil record shows the appearance, change, and then the extinction of many organisms, highlighting the change there, right? Species are changing, organisms are changing, new species are appearing, old species are disappearing. We see this all preserved in the fossil record through adaptation. So we're going to take a little look at this happening, okay? We're going to do a case study on snails. Normally in class you would just do this, but we'll do it together on the video since you folks aren't here. So why snails? They're a great example, okay? They are common and they have been for hundreds of millions of years. So there's tons of them in the fossil record. They are very easily preserved, or relatively easily preserved, right? So you can find a whole bunch of them in the fossil record. Again, they would make a good index fossil probably. It is not uncommon to find the remains of hundreds of generations of snails in one area, which lets you look back and say, okay, what were snails like a long time ago and what were they like all the way up to now? That's really good for studying the history of morphology and the history of adaptations in a species. What's a generation? It's just a single step in the line of descent. So, for example, grandmother, mother, and daughter, that's 3 generations, right? Grandmother's 1, then she had the mother, so that's now 2 generations, and the mother had a daughter. That represents 3 generations now. Another reason snails are great, they have pretty short lifespans and therefore they can adapt relatively quickly. We'll talk more about why in the next topic video, but just reinforcing the idea that snails are a really good way to study this, okay? This is why snails have been around so long. Snails have been around since the Cambrian, right? So basically since the first time that complex life appeared, we've had snails, and they're still here, tons of them. So they've experienced what we call evolutionary success. Basically means there's a bunch of them, they're doing great, and they've been around a long time. So if you do have your textbook, you can follow along at home, although you don't necessarily need it. All of the stuff you need is in the notes here, okay? So in a forest habitat, there exists a species of snail that shows variation with respect to the trait of coloring. So variation is a very important concept to what we're going to be talking about, but it's basically just if you vary something, it means you have different versions of that, right? Variation. If there's a variety of ice cream flavors, you have a bunch of different ice cream flavors. So it's no different here. Variation is just differences in a particular trait between individuals within a population. So for example, there's tons of examples with humans. One we could think of would be that humans show great variation with respect to the trait of hair color. You could have black hair, brown hair, red hair, blonde hair, okay? Same for eye color, brown eyes, blue eyes, green eyes, gray eyes, right? They're all options. That's variation, different options with respect to a trait, the trait there being eye color or hair color. So pick a trait, and if there's different versions of it, then the species is showing variation with respect to that trait. Okay, so in this snail population, there is variation with respect to the number of light bands on their shell. Just to show you what we mean by the bands, you could have no bands, although as you'll see, no snails really have those just yet. And then if it has bands, the bands look like this. So the number of white bands is the trait here that we're talking about, that there exists variation. So snails have different numbers of white bands. There's variation in that trait. And so in the initial forest habitat, which contains a mixture of tall grasses, small trees, and shrubs, that's important because, again, adaptations have to do with the environment you find yourself in. The number of snails that have 0, 1, 2, 3, 4, and 5 light bands is shown in the graph on the left below, okay? So this is the graph here. This is showing us before, basically, right? So you can see no snails have 0 bands. Some have 1, even more have 2, a few have 3, and not very many have 4. So it looks like most seem to have 2 white bands, okay? Then it says that after many years of climatic changes, in other words, climate change, it causes the low shrubs and trees to die off, leaving only grasses. And then we come back and we count up the snails again and we count their bands. And this is what we see this time. We see now that, look, what used to be very popular, having 1 band, has become very unpopular, right? The whole graph has kind of shifted this way. 2 is still pretty popular, but it's not the most popular anymore. It's now more popular to have 1 more light band on your shell. There are 3. 3 is now the most common number of light bands on a shell. And 4, which used to have barely any, has a whole bunch now. It's actually the second most popular. And some snails even have 5 light bands on their shells. So we've seen a shift with respect to this trait. The most common version of that trait now is to have 3 white bands because of a change in environment. Interesting. Okay, so after the climatic changes result in the removal of most shrubs and trees, explain what advantage in avoiding predators banded snails have over unbanded snails. So why would snails with light bands on them now do better against predators than ones without them? Well, if they have light bands, they kind of appear lighter, right? If they have fewer bands, then the darker part of their shell dominates and they're going to look darker. So before it seemed like it was good to not have that many bands. Now it seems like it's good to have more bands. What changed here? You got to think a bit about the environment changing. So maybe write down your own thoughts, pause the video. But I'm thinking, well, if you take all the shrubs and the trees out and you just leave grasses, You've just removed all the shade from the ecosystem, right? Now the sun is beating down. It's a very light ecosystem. So if you are dark, you're going to stick out like a sore thumb. You want to be lighter as a snail so that some bird can't see you as easily and pick you up. Right? Predators are not going to be able to find you as easily. All of your two striped snail brothers are going to get eaten instead of you while you're hiding literally in plain daylight, right? That's why you're able to hide, is because it's lighter out now and you are lighter. So, if more banded snails survive predators, like we just said it would, what effect do you predict this will have on the number of banded snails seen in future generations? So, we're going to talk more about this next topic, but you probably have a general idea of how inheritance works already, right? Do you kind of look like your parents or your brothers or your sisters? Did you kind of get their eyes or their hair or their nose? Even your grandparents, right? Yeah, you kind of do, right? So you probably already have a gut feeling that you inherit traits from your parents. So if there are more lightly striped snails surviving, what do you think the next generation is going to look like? It's probably going to have more lightly striped snails because guess what? Those are the ones surviving to now have babies, and their babies are going to look like them. Right? So essentially, you will see more banded snails in the future. The light stripes seem to be a good thing. The light stripes protect you from predators, which means you're more likely to have babies, and your babies are probably going to look like you. In other words, have the same amount of stripes. We won't go too far into it now because this is tomorrow's topic, but you can now imagine, hey, all those lighter striped babies, they also have an advantage. So they're going to be the ones that grow up to have more babies too, right? Fast forward a few generations, you can probably see where we're going here. Okay, suppose a mutation, we'll see that word more later as well, introduced into the population, produced snails that were a solid dark brown color with no banding, no stripes at all. Would the snails resulting from the mutation be at an advantage or disadvantage in the new tall grass environment? After a year, what would you expect the population of dark brown snails to look like? So you tell me, what do you think? These dark snails now, in an environment where there's no shade, how are they going to do? Is this something that's going to give them an advantage, or is this going to give them a disadvantage? It's going to be a disadvantage, right? They're going to stick out like a sore thumb. Birds are going to see them right away, pick them up, eat them. Okay, so if you came back in a year, what would you expect? Well, do you think there will be very many of these dark brown snails left? Probably not, right? They're not going to be surviving to reproduce very well. They're not going to be having a lot of babies. You would probably see this trait get eliminated pretty quickly. Okay, but one more question for you. What if the shrubs and the trees grow back? Now, do you want to be a dark brown snail or do you want to be a lightly banded snail? Well, if the shrubs and the trees grow back, there might be a lot more shade, and it might be a good thing again to be a dark snail with no bands. So we'll just say that. Maybe if there's another change in the environment, this could become a beneficial trait again. Okay, so the way the ecosystem is now, disadvantage. But if the trees and shrubs grow back, maybe an advantage. Okay, so we're kind of starting to get into the idea here that populations change over time, right? We were seeing here that the snail population, its traits were changing over time. They were going from fewer bands to more bands because the environment was getting lighter. So it's clear from the fossil record that definitely species do experience changes in their traits over generations, right? We can even see it happening in our lifetimes because many generations can occur of shorter lived organisms like, well, snails, right? Or insects, or to the extreme level, bacteria, even, right? They can evolve in a matter of a few days. So these changes can even lead to speciation, okay? What is that? It's the branching off of a new species. It's when a new species is created. So a recent example, or a relatively recent example, is the speciation of dogs, right? They were once wolves. We artificially selected them, it's called. We took them, we breeded all the characteristics we wanted, and eventually we did it so much that dogs were no longer the same species as wolves. A dog can no longer breed with a wolf and have a baby, right? We speciated them artificially, not naturally. Speciation is just the creation of a new species, basically, for whatever reason. There are two main mechanisms through which these changes emerge. Changes being the changes in the species traits or even the creation of a new species, okay? The first is gradualism. Gradualism is kind of what it sounds like. It's gradual. It's slow, it's steady, it's constant, okay? but it's always sort of happening a little bit. It's like the hour hand on a clock. It's always moving, but you can't even really tell, right? It's a lot like uniformitarianism from our geology unit. And then the other one is punctuated equilibrium. Think of like a sentence. What goes at the end of a sentence? Punctuation. So what punctuated equilibrium is long periods with very little change, not much going on, and then suddenly major changes, okay? This is a lot like catastrophism from our geology unit. Nothing's really happening. For the most part, things are staying pretty much the same. And then boom, in just a few generations, big changes. Okay. Why would you have stuff like that? Well, sudden changes to the environment, kind of like we saw with the snail, right? There was a change to its environment. Shrubs and trees died out. And so, in just a few generations, you saw a shift in the population. The idea behind punctuated equilibrium is that until something makes changing advantageous, things probably aren't going to change much unless there's a really helpful but random mutation that we'll talk more about later. Okay, so almost always it's a response to a sudden change in an environment. So this picture kind of visualizes gradualism versus punctuated equilibrium, right? A long period of nothing really changing, and then suddenly a big change, a big drastic change in morphology, versus gradualism, where it's kind of always changing just by a little bit. You might not really notice it happening, but fast forward long enough and you get some speciation or differentiation with respect to traits. I think of punctuated equilibrium like a staircase. Okay, so no change, no change, no change. And it helps you remember by thinking of punctuation too, right? So, like you could say the sentence is giraffes have short necks, and then something changes dramatically. Boom, punctuation, big change. Maybe all the short trees die out. And now, over a few generations, giraffes get slightly longer necks, and that's the new sentence. And then, boom, punctuation at the end of the sentence. Maybe all that's left now is even taller trees, right? And so giraffes relatively suddenly adapt with longer necks through a process we'll talk about next video, right? And it's long periods of no changes. And then all of a sudden, relatively fast changes because of a change in the environment, usually. Okay, so punctuated equilibrium are like stairs, whereas gradualism is more like a ramp. Okay, you're always changing a little bit. It's just slow, steady, and over enough amount of time, you'll get to the same place the stairs got anyway. Unlike in our geology unit, where we kind of decided one was definitely more right than the other, most biologists nowadays actually agree that both are occurring. So gradualism is kind of always constantly happening, but punctuated equilibrium will suddenly cause big changes. So, yes, gradualism is occurring, but the big dramatic changes that you can really notice are going to come from punctuated equilibrium because all of a sudden, boom, big change, right? It's kind of like, yes, both the hour hand and the second hand are telling time, but you can notice the second hand because it's a little more sudden. You can see it happening, right? The hour hand is always there, always telling time, but it moves a little more slowly. So both are occurring. So I'll show you a quick video illustrating how evolution, while a slow process, yes, can be relatively quick, a lot quicker than people think. Okay, I'll show you this video here. So sudden change in the environment, so a different trait became advantageous, and over just a few generations, that trait became the more commonly expressed one. Last thing we're going to look at before we really jump into evolution in tomorrow's topic, okay? This little case study with some what we call peppered moths. So during the Industrial Revolution, industrial waste darkened tree trunks and killed off the lightly colored lichens. So we're getting tree trunks that suddenly become darker and lichens that are light, well, dying off. Light moths became rare and the dark moths became abundant. So in 1819, the first dark moth ever was seen. So light moths were way more popular. No one had even seen a dark moth. But by 1886, dark coloring was the far more common morphology. There were way more dark moths. Eventually, light moths were common only in areas that were far from industrial cities. So essentially, you didn't see dark moths near these industrial cities. The cause of this change was thought to be selective predation by birds, which favored camouflage coloration in the moth. So you could probably have thought this out yourself, right? If you're a dark moth on a dark tree, harder for the bird to see you, right? Imagine you're a bird rolling up to this tree. Where are you going to go? Easy target, right? Go for that guy. He's there. You might notice him, but you're a lot more likely to see that guy and eat him right away. Whereas before the Industrial Revolution, it's the total opposite, right? You want to be that light peppered moth. And so over time, with this happening, with the dark moths surviving to have babies and the light moths getting eaten before they can have babies, you're going to see a shift in the population towards the dark moths being favored near the industrial cities. Okay, so this question asks, are these changes in pepper moths better examples of punctuated equilibrium or gradualism? And explain. So pause the video, try this one on your own. But what do you think? Is this just slow, steady, everyday changes that always kind of occur? And if you fast forward long enough, you start to see this change? Or is this relatively quick changes happening in a population over just a few generations because of some sudden change in the environment that made a trait that used to be disadvantageous suddenly now advantageous? Which one? It's the second one, right? We've suddenly had a change in the environment. Trees used to be light, now they're dark. Being light used to be good, now being dark is good if you want to hide from predators. So a sudden change in the environment has led to a shift in what is advantageous, and therefore who gets to survive more and have more babies, right? A shift in the population will occur. So this is textbook punctuated equilibrium. So for starters, it was relatively fast. In less than 70 years, this occurred, right? That's pretty quick when we're talking evolution. But yes, punctuated equilibrium can happen quickly, but that doesn't make it punctuated equilibrium. It's punctuated equilibrium because it was a response to a sudden change in the environment, right? Suddenly, a trait that used to be a disadvantage was now an advantage. And so organisms with that trait are more likely to survive and reproduce, which again means they're likely to make babies that look like them, who are also more likely to survive and reproduce. And we'll get into all that fun stuff tomorrow. Okay, so at the end, you should be able to answer these. If not, maybe go back in the notes or in the video lesson and see if you can find the answers. What is variation? What are adaptations? Why is an adaptation likely to start appearing more in future generations? That's one that we will be exploring in more depth tomorrow, but you should have a basic feel for that right now, okay? What is gradualism and what is punctuated equilibrium? You should be able to compare and contrast those two. Okay, if you're looking for practice with this stuff, try the topic 2 section of this week's practice assignment.